So we were talking about the idea of light having wave-like properties. In reality, it's got properties of a particle as well. So that makes the photon kind of this strange, weird particle that's a wave and it's a particle at the same time. And so what we want to look at today is look at the wave-like characteristics. And in particular, two different types of expressions. One that allows us to convert between the wavelength and the frequency of a photon. And the second one that allows us to convert between that wavelength or that frequency and the energy that that photon is carrying or transmitting. So we're going to break this problem up into two parts. We're first going to look at how to do this particular conversion between wavelength and frequency. Then we're going to take that and we are going to calculate the energy of that photon from that. So the first step is we're looking at a 450 nanometer photon. And what we're going to find is that when we do this transformation between wavelength and frequency, we know that those two values, the values for those two characteristics, wavelength and frequency of a photon, when we multiply them together, it equals the speed at which that particular particle or that particular wave is moving. And so in the case of light, that is the speed of light. Speed of light is in meters per second. It is not in nanometers per second. So we are going to have to convert this to meters first before it can go in that equation. So remember that there are a lot of nanometers, 10 to the 9th nanometers to be exact in 1 meter. And when we do that particular transformation, we get 4.5 times 10 to the minus 7th meters. That would be our wavelength. 4.5 times 10 to the minus 7th meters. And you might say, oh, Dr. Ramsey, you're losing out on a number, on a significant figure. But remember, we started here with 2. That 0 doesn't count. And we end up with, when we write a number in scientific notation, we write only the digits that are significant. So we end up with our 2. Now that allows us to go and take this expression and use it to calculate the frequency, knowing only the wavelength. So we've got our speed of light, c, is 3.00 times 10 to the 8th meters per second. And that's going to be equal to the wavelength that we just calculated, 4.5 times 10 to the minus 7th meters per second, meters, and that's going to be multiplied by the frequency. So now we can solve using basic algebra. We can solve that frequency, and we find that frequency is 6.6667 times 10 to the 14th hertz. Remember, hertz is the same unit as 1 divided by second. So you could have hertz, you could have 1 over second here. Either one is the exact same unit. Now, going forward, we want to be able to calculate what the energy is using this expression. Before we do that, I want you to think about which of these two expressions we're going to use. Energy is equal to Planck's constant times the speed of light over the wavelength, or it is equal to Planck's constant times the frequency. Which one of these would we choose? Well, we know the frequency and we know the wavelength, so in theory we could choose either one of those. However, I am going to choose to use the wavelength because that number is given in the problem. I don't have to worry about rounding wrong or getting the correct number of significant figures. I am just going to choose the number that I started with. So I am going to choose the expression energy equals hc over lambda as opposed to energy equals Planck's constant times the frequency. I'm going to choose this portion of it and use the number that I was given. Then if I calculated this incorrectly, it's not going to mess up the rest of the problem for me. Now, one thing that we sort of neglected is we have this number. I put a whole bunch of digits here, but in reality, it doesn't have this many significant figures. So how many would it have? Well, I had a number that had 3 to begin with, and a number that had 2 to begin with. And boy, does scientific notation, numbers given to you in scientific notation really help with significant figures, because only the significant figures should be included. All right? And so I'm going to end up with a number that should have 2 significant figures, so that frequency would be 6.7 times 10 to the 14th hertz. That'd be the answer. That would be the frequency for a photon with a 450 nanometer wavelength. Now, what I want to do is I want to move on to calculating the energy. And so I said, all right, I'm going to use energy equals Planck's constant times the speed of light over lambda. Remember, Planck's constant, 6.626 times 10 to the minus 34th joule seconds. And remember, speed of light, we just used 3 times 10 to the 8th meters per second. So I've got Planck's constant, I've got my speed of light, I know what the wavelength is, so I can calculate the energy. So energy equals 6.626 times 10 to the minus 34, and speed of light 3 times 10 to the 8th meters per second. My wavelength, 4.5 times 10 to the minus 7th. And if you're sort of following along there, this is joule seconds, this is meters per second, and this is meters. So the seconds are going to cross out here, the meters are going to cross out here. I'm left with a unit of joule. Joule is a unit of energy. So I plug this into my calculator, and I should end up with 4.417 times 10 to the minus 19th joules. Okay. And now how many significant figures? Well, I start off with a number that was 4, and I multiplied it by a number that had 3, and I divided by a number that had 2. All multiplication and division. So I'm just going to choose the smallest number, that would be 2, of those 3, 2, 3, and 4. And so it's going to be significant to the 1, 2, to that place right there. Look to the right of that digit, it's a 1. 1 is less than 5, so I'm going to leave it as it is. And energy would be 4.4 times 10 to the minus 19 joules. So in reality, doing these problems, photon, wave, frequency, wavelength, energy problems are pretty much plug and chug type problems. We find the correct equation, we plug everything in. As long as we do the math correctly, the algebra correctly, we should get the right answer.